In 1859, the sky caught fire. Not from war, not from a volcano, from the sun. For a few days in September, the aurora, the lights you'd normally only see near the North Pole, showed up over Cuba, over Hawaii, over the Caribbean. People in Boston said the sky glowed so bright at midnight you could read a newspaper by it. And then the machines started screaming. Telegraph wires, the entire communication backbone of the 1800s, surged with so much electricity that operators got shocked at their desks. Some machines kept sending messages even after they were unplugged from their power source. The sun itself was powering them. Here's the part almost nobody knows. If that same event happened today, it wouldn't just light up the sky. It could black out continents. And by the end of this video, you'll never look at the sun the same way again. Most people think of solar flares the way they think of lightning. Flashy, dramatic, but ultimately harmless from 93 million miles away. The sun does its thing. We get a pretty aurora once in a while, and life goes on. Space is big. Earth is small. Surely we're too far away to actually get hurt. That's the story you've probably absorbed without ever really questioning it. Here's the crack in that story. The sun isn't just a light bulb sitting quietly in the sky. It's a churning ball of plasma that occasionally rips a piece of itself off and hurls it directly at us. Billions of tons of charged particles moving at speeds that make a jet look like it's standing still. And in 1859, one of those pieces hit Earth almost head-on. That event has a name, the Carrington Event. It's the strongest geomagnetic storm ever recorded. And here's what should keep you up at night. Scientists believe storms like it happen on a cycle, not if, when. So today we're answering 3 questions. What actually happened in 1859? How does a burst of light from 93 million miles away fry electrical equipment on Earth? And the one that really matters, what happens if the next Carrington event hits a world that runs on satellites, power grids, and the internet instead of telegraph wires? So let's go deeper than anyone has ever taken you before. The sun isn't solid. It's a boiling sea of plasma, and its magnetic field gets twisted and tangled like headphone cables in your pocket. Every so often, that tangle snaps. When it does, 2 things can happen. First, a solar flare, a burst of light and radiation that reaches Earth in about 8 minutes, the same time regular sunlight takes. Second, and far more dangerous, a coronal mass ejection, or CME, an actual eruption of solar material, billions of tons of charged particles flung out into space like a cannon blast. On Carrington's Day in September 1859, astronomer Richard Carrington watched a flare so bright it looked like the sun had a scar on its face. 17 hours later, the CME hit Earth. Normal CMEs can take 2 to 4 days to reach us, if they're even aimed at Earth at all. Space is huge, and Earth is a small target. But the Carrington CME was moving so fast and so directly at us that it covered the 93 million mile trip in under a day. Think of it like this. Most cosmic weather is a distant storm you can track on radar for days. This was a storm that appeared on the radar and made landfall before you finished your coffee. When that wall of charged particles slammed into Earth's magnetic field, it didn't just bounce off. It compressed our planet's protective shield and dumped some electrical currents into anything made of metal that ran for long distances. In 1859, that meant telegraph lines, thousands of miles of wire, acting like one giant accidental antenna. But here's the part that nobody talks about. The damage in 1859 wasn't really about the sun being unusually powerful. It's that Earth, for the first time in history, had just built a nervous system made of wire. The Carrington event wasn't the strongest possible solar storm. It was the first solar storm to meet a planet with an electrical grid. And that timing is exactly why modern scientists are worried. Here's the did you know moment. The actual danger isn't the particles hitting you. You and I are protected by Earth's atmosphere and magnetic field. The real danger is induction. When a magnetic field fluctuates rapidly near a long metal conductor, a wire, a pipeline, a power line, it induces an electrical current in that conductor, whether anyone wants it there or not. It's the same basic principle that makes an electric generator work, except instead of you controlling the current, the sun is. In 1859, that meant surging telegraph lines. Today, it means power transformers the size of school buses sitting at the heart of national electrical grids built to handle predictable current, not a sudden, planet-wide surge dictated by a solar storm. So the question becomes, if this happened once to a world with telegraph wires, what happens when it happens to a world wired for everything? Here's what most science documentaries tell you. The Carrington Event was a freak, one-time cosmic accident, largely irrelevant now because we have better technology. Case closed, moving on. Here's what power grid engineers actually lose sleep over. A Carrington-level storm isn't rare on a geological timescale. It's expected. Storms of that intensity are estimated to occur roughly once every 100 to 150 years, and the last one to actually hit Earth dead-on was in 1859. We are overdue, not because of superstition, but because that's simply what the statistics of solar activity suggest, and we've already had a close call. In July 2012, a CME, every bit as powerful as the Carrington Event, tore through the exact orbital path Earth travels, except Earth itself was about 9 days away from being in that spot. 9 days. If that CME had launched a little over a week earlier, engineers who study it believe it would have caused a global technological blackout, with damage estimates running into the trillions of dollars and recovery time measured in years, not days. Wait, it gets even more interesting. The real vulnerability isn't your phone or your laptop. Small electronics are actually fairly resistant to this kind of event. The vulnerability is the giant, specialized transformers that keep national power grids running. Machines that are custom-built, take months to over a year to manufacture, and aren't sitting on some warehouse shelf ready to ship. If a severe geomagnetic storm fries enough of these at once, you're not looking at a blackout that gets fixed in a weekend. You're looking at a blackout that could last months, because there simply aren't enough spare transformers on Earth to replace them quickly. Here's the historical case study that proves it can already happen at smaller scale. In March 1989, a much weaker geomagnetic storm than Carrington level knocked out the entire power grid of Quebec, Canada, in under 2 minutes, plunging 6 million people into darkness in the dead of winter. That was a moderate storm. Carrington level is estimated to be many times stronger, and here's the single most mind-blowing fact in this entire video. A storm strong enough to threaten global power grids has already been recorded in human history. Twice. The Carrington Event in 1859 and ice core samples from Greenland and Antarctica reveal an even more extreme radiation spike around the year 774 AD, an event so massive that scientists still debate exactly how strong the eruption was, because nothing in the modern era comes close to it. You've probably never thought about this, but every time your phone shows you a location, your bank verifies a transaction, or a plane crosses the ocean, it's quietly relying on satellites and precise timing systems that are sitting exposed in space, directly in the path of solar storms. GPS isn't just for directions. It times bank transfers down to the millisecond and helps keep the power grid itself synchronized. A severe solar storm doesn't just risk the lights going out, it risks the systems that coordinate how the lights, the banks, and the flights all talk to each other. Next time you check a weather app before a flight, know that airlines already reroute polar flights during strong solar storms, because radiation exposure at high altitude near the poles spikes, and high-frequency radio, communication that pilots rely on over the ocean, can drop out completely. This already happens, quietly, several times a year with smaller storms. There's a modern application already being built specifically because of this threat. Space weather forecasting has become its own serious field. Government agencies now monitor the sun continuously with dedicated satellites, giving grid operators a warning window that can stretch from tens of minutes to, at best, about a day, depending on the type of event. That's not a lot of time, but it's enough to intentionally shut down or reroute parts of a power grid to protect the giant transformers we talked about earlier, the same way engineers might safely idle a machine before a predicted overload. And here's a surprising comparison. This same principle of induced current in long conductors is why old CRT television screens sometimes distorted during aurora displays, and it's part of why undersea internet cables and long oil pipelines both have to be engineered with corrosion and current protection in mind. The same physics linking a solar storm to a blacked-out city also links it to a pipeline in Alaska. One principle, wildly different consequences, and this is just the beginning of how deep this goes. Now here's something that most people never connect to this topic. The same solar activity that threatens our grid is also the reason the aurora exists at all, and studying tree rings and ice cores has let scientists build a history book of solar storms going back thousands of years, written entirely in radiation, long before anyone had a telegraph, let alone a satellite. Think of the sun like a moody, cyclical drummer, keeping a beat that rises and falls roughly every 11 years. That's the solar cycle. Most years, the beat is quiet, but every so often the drummer goes wild, and that's when flares and CMEs become far more likely. We're not guessing at random when scientists say we're due. We're rereading the rhythm of a beat that's been recorded, one way or another, for centuries. That's the setup for the real takeaway of this whole video. The danger was never really about the sun. It's about how much of our modern life we've this quietly plugged into a system that has no idea a solar storm is coming until it's already here. Let's bring it all together. In 1859, a solar storm hit a world with telegraph wires, and it lit up the sky and shocked operators at their desks. In 2012, a storm just as strong missed Earth by only 9 days, and right now, engineers are racing to build early warning systems for a threat that isn't it's overdue. Here's the big takeaway. The sun isn't just a light in the sky. It's a slow, patient reminder that our entire modern world runs on infrastructure that was never designed to survive a direct hit from the star that makes life possible in the first place. Now I want to know, did you ever realize the sun itself could be one of the biggest threats to modern technology? Drop it in the comments. In our next video, we're going somewhere even most engineers have thought about, the hidden engineering inside the systems built to survive disasters we can't even predict yet. Because at Logivra, the more you understand the logic behind the world, the less anything in it can catch you off guard.